let's finish the buffer overflow stuff so we can get back to doing some boxes, because I want to do that. Take control of EIP. Yeah, let's actually put the marker here. Marker. Actual stream start. Yeah, so now we have that added. Then I start coughing when I'm going to start reading. That's typical, right? Yeah, I'm kind of sweaty. So let's get started. Stack-based buffer overflows on Linux x86, and we've been doing a few of the pages here, and now we're at the actual exploit section. So this is mostly theory, and this is why I clicked typically update it. Let's skip it for now. It wanted to update to VMware. So I'm thinking I will probably need that, as it has this cube here. One of them I'll start reading again. Take control over EIP is the current one, the first of the exploit here. One of the most important aspects of stack-based buffer overflow is to get the instruction pointer EIP under control, so we can tell it to which address it should jump. Sorry. Oh my. Oh, this feels horrible. Sorry for being so very out of shape, right? I'm out of shape, out of streaming shape. Taking the EIP under control, so we can tell it to which address to jump. This will make the EIP pointer to the address where your shellcode starts and calls the CPU to execute it. And I'm actually going to hop the and read my description here again. So, buffer overflow is when vulnerable code writes over a bigger section of memory than it should. The C functions, get, stir copy, and so on are examples of functions that doesn't check the available space before writing. First, we need an input to test for overflow. It can be any kind of input: user input, command line arguments, network commands, environment variables, and so on. We can perform basic tests where we try different input, increasing the size, like in some examples we're piping Python data to the program, or as arguments here. Here this will be in the input stream for this program, and when it asks for input, it will be sent as it will be read from there. Program, here we start it as an argument instead, and we use these backticks, or better, dollar parentheses. You don't have to mess with messy characters. The third one, I'm curious. So, when we find a buffer overflow vulnerability, we need more information. Hopefully we can run the program in a debugger or attach to a process with a UI debugger like EDB. Linux or immune to debugger Windows. Tools, Linux. Windows. And so far we're mostly checking out Linux. And why is this one here? So it's like an example. It's still a bit odd. It's an example use of one of these. Well, I added some space just. We want to see what part of the input we gave ends up in memory, if we get a buffer overflow, that is. You can make a string to test both manually or... okay, why did it put this here? To do this, Metasploit or use a tool. Metasploit has two useful scripts. One to generate non-repetitive string, and one to give us the offset position of a part of the string. And I have added the relevant command line parameters, or is it all of them? I don't remember. I did help on them. Exploring memory, the stack and heap. Yeah, so we're going to add stuff here. So the question is if we should do this now as the focus, because this is what's important. And or should I just link to GDB and R2? So I feel this is the worst stream ever, but I need a bathroom break already. Sorry. At least I'm not muted. So yesterday I was like highlighting a few old streams that was almost timing out on Twitch, and one of them I fixed the mute problem because I muted myself twice. I think one of them I just touched the mute button and my buttons by mistake. But now I have a sign saying whatever I mute, if I mute the hop up there. Yeah, I'll be right back. I'll actually leave the door a bit open because it's really warm in here. Almost 28.5 now. So let's see. Yeah. So collecting all the information from the different sites and everything, the whole point of this, you know, learning it and making good notes. I really feel like I have not had time to focus on this, unfortunately, lately. But now, I'm going to. So, unless I get an SMS that ID is finished. Yeah. So, I just clicked mobile live dashboard here. So, now let's get started. Or rather, whatever this is. The third start? Yeah. So, we have explored these tools, and this is a short dump one. But what we would need to do, exploring memory, really this one should be down here. Yeah. So let's actually hop that down. We can use different tools. I guess to explore memory. And to debug and step through program execution. Should I also remove the? I think it's too much. So, exploring memory, stack and heap. We can use different tools. Now this is more like a new sentence. And we don't have headers. It's just a part of basics, which is a 3 level header. So we can do this as a level 4 header, or even level 5, because we haven't used headers before, so let's not make it pop up too much. We can use different tools to explore memory and to debug and step through execution. The simplest might be dump. More complex with almost infinite possibilities are well, GDB and R2. Tools like so let's give it a few examples. We might have stuff further down too. So basic notes there. That's from long ago. I just put it all together, you know. We should make an assembly like list too. So let's see, where are we here? So we're in the right place. Why are these in images? That's just... So this is just the images for those. Okay. Because they're down here, right? So these are the first THM. I think this might be from there. The first THM stuff on x86. Processor architecture and assembly. They were very basic. So, but they also had this nice thing that you could, like, it was like, step through this instruction, see what happens. It was like the EDB in like fake mode. So if I scroll up to tools, you have EDB here. Let's do graphical. And let's remove that. It's not really that important. So much to scroll through here too. So this is the most basic buffer overflow example. Do we have an example here? No, maybe we should. Like adding it here. This is probably the spot for it. And so the notes that are attached there, they're not really like, no, here. Example. One, two, three, four, five, six. Meaning we can only minimize it if we have a header after too, so let's skip that. Yeah. So this is not a good example. If we have null here, we'll get this problem. I don't know. It's just a bad example. Whatever. I guess. So these are really... Is there a way to set the font without typing code? No, I'll have to do it myself. I think it was 2 that we used. So we have tinier text. The new line is big though. Oh, that looks funny. So it's more obvious that belongs to the image, right? Yeah, so Obsidian isn't perfect. So now we have an example of one of the functions here that breaks, right? So it's easier to understand. Exploiting buffer overflow. And now we have a header name for this. And I guess it's still basic, right? Wow. First we need an input test for overflow. Let's grab my examples here. We'll make examples as we do them, right? We'll just add them here. So examples, GDB. Examples, R2. R3, it's even there. Yeah, so this is the adding 30 characters, then doing this thing, right? 48 B9. Yeah. So this is from the Try Hack Me room as an example, and I disassembled it to see what it actually does. And then there's text explaining. And let's remove the space here. A book tip. Oh, right. So this is from Al's stream, I guess. It is a stream that he's got on YouTube. Memory layout. This was a more detailed image. User stack, shared library regions, runtime heap. Let's put this one a bit up. This is good to start with this actually, because I need to like get into this again. Memory layout. Yeah, that's a base, right? These functions are, this is what the vulnerability really is. Here, information about the memory, and I had more basic stuff here. The stack. Then we have assembly stuff here, which shouldn't really be here. And what image is that? We'll see. I have stuff in memory here now. So we're on. we need to go. Maybe I should remove one square from these. So this one is 3. This one should be 4 then. This one should be 4. And this is why I started adding headers. it's also easier to read, right? So memory layout, and these should be fine now. The stack, oh my, the heap. So grows downward, contains program counter, saved register, other info. Data is pushed. I was like, what? Pushed onto stack and popped off. Grows upwards. I was like, should I do the lost in first up? But whatever. It's not really true, is it? With variables for functions and function frames. Grows upwards, contains dynamically assigned memory. Let's add that frames. Stack frames. It wasn't long ago I didn't know about them. I was like, what? Stack frames. Let's leave it at that for now. Right? And let's put the image first. Because we want an image first, right? And let's make it a bit tinier because it doesn't have to be this big, it just gives us more scrolling. So, is that too tiny? It's hard to read, right? So, I guess that's good. So higher memory addresses and 0. I believe that these other images are better, really. So we have this other image too. So what if I add an image here? Yes, it works. I was like, can I put them next to each other? That's good, right? Let's actually, I guess we'll do 75. And we do space before, so we have a tiny bit of space in between there. So this is generally memory, and this is stack top and bottom. We're going to add more images there. Where could I have images? I actually think that this one is good, but yeah, it's just randomly here. Let's get it. I can see buffer overflow too there. So this one needs a bit of size fixing too. Oops. Let's do a bit bigger. 700. There. So if you read this through, you don't know what ESP is, but so I have one with this. If we go to Protostar Stack 2, no, it's not that one. I was just curious about for the name of the file. It's just called 2. Is it this one? So this is us experimenting with GDB. So learning slowly, getting more and more knowledge about this, right? So we have Track Me Rooms. THM rooms and other exercises. Real world buffer overflow examples. Yeah, I'm kinda. This is not all I want to add in all the places, you know? But now this is not like as messy. So I don't want to have assembler in here. So this is not sorted and ordered, so I'll just dump it. So this is kind of like, this is the mess left. I don't even know if it's spelled like that, right? And so we have this still. Yeah. I guess there's a space. This is almost where we are in up here. So this should really be before. Let's leave it at this for now. This is not even right here. It's piped to the program, and this is just like structure of the data of the input. Input, not in out. Knob, number of knobs, shellcode, random data, number of random data. Oh, memory address. Okay, yeah. And this is just split into lines by obsidian, because this is the only space, so it looks a bit funny. So this is for an example where we have seaweed on the binary. So if we open a shell, we'd have other permissions. But when I run one of those, I need to tell it to bring the permissions. Does this do that? How? It's not like complete, right, is it? And I also think that the Metasploit ones are much longer, right? Crazy much longer than this is for Hack Me. Source Tisha. So we need to add info everywhere now. It's not as well, it's more finished, but it's also less. So we have these in other places. Right. So now we're on SQLi suddenly. Let's actually close those. No, yeah, that was the only one. The rest of it is buffer overflow, assembler, security features. So obviously this was Windows, right? But it says something about the time when we started thinking of this anyway. And this is on my Kali machine. So if we were to run this now on my newly started machine here, right here, and we still have a 2 now because it's obviously reset, and that's what I wanted to test now. So this is reset at when is it reset? Is it separate for every terminal? I'm assuming, but so I feel it's nice that we're progressing, but where did I type the password if it wasn't here? It's not a secret password. Let's see. I'm copying these since they're kind of long, and I don't want to waste time. So so if we now exit, I might like typing chat now. well, so if we run this again now, it's 0, and we cannot sudo run this one as it doesn't work. I don't know if it is echo that if it's that there we have the arrow. I think that everything should be run within the line with the sudo permissions, right? But it doesn't work anyway. I tested. So now we have this here. Let's open up another tab, and let's run the cat command again. We have 0 here too. So let's open another version of the program, separate instance. We have 0. This is seem to be like everywhere in this machine now. So if we do restart it, then that's when I assume that will be reset. So, and this is what I was going to type, but I wanted to have it 100% certain. Because it wasn't complete before testing this, right? Is it password 123? What do you think I have as password? So no. I had to copy it again. Yeah, and it works now. We have 2 again. So we're back to safe mode. Or ASLR. Yeah, I was thinking, don't I have what it is? But I do. Address space layout randomization. Randomizes where everything is stored, makes exploits less reliable. Countermeasures. Possibly leaking memory addresses. Might not be possible. So this is like something we might want to disable when we test stuff. And learn the basics of buffer overflow. So that's why we have this document. So let's actually, I think where the notes are kind of sorted, not the assembler ones, but the buffer overflow one is like in an okay order now, and I know where to put stuff I learn, you know. So if there's new stuff here or something that I have not got in my notes, so the fact that EAP is our target, right? So it's the next step here. To test, I'm like, do we have buffer overflow, right? Test input. And that's what this section is about, testing input. And here is suggestions for the programs. We want to see what part of memory what we sent ends up. And then we have on exploring memory that we will add stuff, examples there too. And then we have using shellcode. Hello, welcome in. Good afternoon, everybody. So we're doing buffer overflow today. So right, so we need to explain why we have a NOPS here, right? So we want to put code in memory, and then redirect execution to this memory. Nah, it's not on voice. So if you start talking about buffer overflow, then I will turn it on, okay? So teach me stuff or ask stuff about buffer overflow, and then I will turn TTS on. Structure of the input. example. We use a number of NOP instructions to decrease the to make the address. My god, is my keyboard dying? Hi. Address easier address of the exploit. Easier to find, to get to. If we have 90 knobs, we don't all addresses within these will lead execution to the shellcode. So, do I need to explain what a NOP is too? Probably. So, structure of the input, NOP, number of knobs, shellcode, random data, memory address. Hello, welcome in. So, we can remove this line. It was from an earlier version here. So here I have disassembled this example shellcode from TryHackMe, so we can see what it actually does. And you can look at my notes yourself if you want to read this now. So let's be efficient and continue. Right. So I thought I had finished fixing the notes, but apparently there was one section more. I'm going to put more text here later, but let's hop now to this. Right, what I was really going to add to note is that the purpose here is to redirect. The next step is to change the value. I don't understand there. No, I don't have TTS on because a lot of people were sending spam. So right now there's no TTS on YouTube. The next step is to change the value of the instruction pointer. That is spam, asking for TTS to be turned on. So I told you the way to turn it on is to talk about buffer overflow, since that's today's topic, right? So no, I'm not getting distracted now. I want to focus on this. You're welcome to stay and learn. This cannot be done directly as it is read-only, but the old value, my god, of the instruction pointer is saved to the stack when execution I'm thinking this is like too much. It's redirected to a function when a function is started. Is called. This address. So I keep misspelling address since the Swedish spelling. This address is saved on the stack and can possibly be overridden. And this is what we're going to try to do. Oh my god, my toes are like squished. The next step is to change the value of the instruction pointer. This cannot be done directly as it is read only. But the old value of the instruction pointer is saved to the stack when a function is called. This address is saved. Oh my, I shouldn't pause. This is where it can possibly be overridden. So that's why I read what I wrote. This cannot be done directly as it is read-only, but the old value of the instruction pointer is saved to the stack when a function is called. This is where it can possibly be overridden. Right? So, but to override it, we need to know the organization and contents of the stack. This is more like an example shellcode that we have here. So it really should have this section up here. And then it continues. So this is just an example. So example shell code then. Shellcode that opens basic shell source track main. The shellcode disassembled. The shellcode disassembled using R2 and commands A and then PDF. And then I have explained it there too. And this is also a image content now, kinda image comment. Where did I have that one? Give me the font. I'll have to type it again. So font size equals 2. And now we'll have to add VRs too, because this will break the if I go down here, we'll all make one line. So there. So I don't know what you're talking about, Alexander. Sorry. So let's just check 4, 5, 5, 4. So be on topic, okay? Message retracted. Yeah, so if you wanna spam stuff, if you wanna mess around, if you do something, I won't ban you for asking me to turn on TTS a million times. But you know, there are limits. I will ban you if you take too much of my time, right? And the stream's time. Yes, I understand what to turn TTS on, but I won't do that as long as you know you're using capital letters, meaning screaming too, right? So you're shouting that, and that's not a nice way to do. So I'm going to ignore you and focus again. So you're welcome to stay and learn things, because I don't think you know this, or you would be talking about this instead of asking me to turn on TTS all the time. So take control of EIP is the next section here on HackTheBox Academy that we have. It's like the third or fourth source of information about buffer overflow. One of the most important aspects of static-based buffer overflow is to get the instruction pointer under control, so we can tell it to which address it should jump. This will make the EIP point to the address where our shellcode, and the uses it one word here, starts and causes the CPU to execute it. We can execute commands in GDB using Python, which serves us directly as input. I'm actually making so I can't see chat anymore because it's annoying me. Next step is to either ban or time you out again, okay? But I would prefer you to stay around and actually enjoy this stuff, right? Segmentation fault. Take control of EIP. So GDB queue, which is quiet, just quieting the license information we get otherwise, both 32. Right, so this is an executable we had as an example before. So I'm going to look it up and we'll just find it where we put it. So we have I would really, maybe I should just delete these pre ones, like music. I'm not gonna have music on here. And the dot ones we can skip. Yeah, so this is HackTheBox Academy, HBA. That's the one. So and CDS. And here we have our bow. So if we just run this, it will get Stack Overflow, right? Oh, right. In case I remember how to actually start the program. We got segmentation fault, we got the buffer overflow already. So let's go back. We have the stuff up. And we also, if I scroll up here, we did not set this, so we know where we are, right? So if we run this in here, so the run command, let's remember my notes. So let's run these things on here. So GDB, and this is what we're running. And it did do Q, right? So I'm going to copy the next line that they run so that we can test exactly the same. No stream crash yet. So starting program with the parameter of this file string line 1 print. Oh, that's a lot of characters. Syntax error, missing parenthesis. Seriously. This is a bad example. So instead of using theirs, let's go to our notes, right? I hope I don't have this problem in my notes. But Python by default on my machine does not do Python 2, which some people's might. Yeah, so I also have the no parenthesis version here, but not here. So this is the one that I actually run on our machine, right? So these are not needed, but I'm assuming, oh right, I put this in the totally wrong place. That's stupid. There. So, and here I also do print with parentheses. So, notes updated. Now let's update this one. The program being debugged has been started already. Started from the beginning, yes. During startup, program exited with code 1. Parse error. Oh. There. So let's just make sure I didn't do the same thing in my notes. Of course I did. Third try. This one was already done, so it's correct. Yeah, the rest is correct. So we do 55 here, or rather we do it down here. Starting program. Thread debugging is using libthreaddb enable, using host libthreaddb generally. Program receives signals segmentation faults, and this is the contents in question. Right, so let's do exactly the same after making the change. Modern security, right? So if we turn off address space layout randomization, let's turn it off and then do this again and see. I'm thinking we might get an address here instead. That's what I'm curious now. So if we quit this, yes, and now we run sudo and we do password, and then we echo 0 to randomize VA space, and then we exit. And do we have it in the history? Kind of think so. Well, I guess we'll just copy. It's the quickest. And right now, I just want to be efficient. It felt we spent a lot of time on crashing. Right? So now, if we run the same command again, gdb qbow, and we do the same play command, or run, my god. I'm seeing a play button, like starting the program, right? So run, and we need to change this. There. So actually reading what I do this time. So we do x55 1200 times, and this print command is run with Python C, and this, the result of this is then returned as a parameter to run, which means it will be debug run. Both are to with this argument. So it's still question mark there. That's interesting to know that there's no change. Okay, so let's continue. We got this, and they also have this. If we insert 1200 use hex55 as input, we can see from the register information that we have overridden the EIP. As far as we know, the EIP points to the next instruction to be executed. Right, so let's also do info registers, right? I think IR. Yeah, same thing, IR. Trying to learn those. Only 55s here. In EIP. So trying to hop to this address. So I'm curious what this is. Maybe it has to do with all the stuff. We'll see if it explains it. I hope so. So if we want to imagine the process visually, then the process looks something like. So we type over here all of the memory, even the EIP, EBP, and EIP. Oh my god, my eyes. Suddenly I'm like, this means that we have to write we have what? This means that we have to write access to. We have write access to EIP. What to do? This in turn allows specifying to which memory address the EIP should jump. However, to manipulate the register, we need an exact number of U's up to EIP so that the following 4 bytes can be overridden without desired memory address. Yeah, I think those YouTube trolls were keeping me awake. If you smell food, maybe. Right? What? There. So we're overriding EBP and EIP here. So we can see it here too, that EBP is also all 5s. I'm thinking, don't I have another explanation in my notes? I miss parts. It's probably these. Yeah, right, we tested this too. So EBP is pushed because it's the old stack pointer. And this is the C2s. Somewhere here. No, not in this one. Yeah, C2's inserted twice. So here we have C2 and here we have C2. I don't think I have much. There's this, of course. Yeah, so EBP, stack base pointer or frame pointer, points to the base of the stack, meaning the top of the last frame. Kinda. Yeah, well, actually. So, now I just wanted pie. It's not very good, I'm just hungry. Yeah, I think we need to put this bit about. Yeah, I think I know exactly what I'm looking for now. It's in here, right? Program structure in ASM. Call. Call does. Function prolog does. Function epilogue does. This is such an important thing. Yeah, let's put this in here. Actually, because it's such an important bit. I'm thinking, should I move it? But it also belongs there. So, but to override it, we need to know the organization and contents of the stack. And how the instructor pointer instruction pointer is saved, and did someone knock? I don't know. I don't think so. It was further away. Is saved there. And then we paste of the stack and how the instruction pointer is saved there. Program structure in ASM. But right now it is 4 level header instead. So we need to to repeat this very important bit, call of a function, and we're assuming that so it pushes the EIP onto the stack, saves the old instruction pointer to the stack, hops to the function's address, and when the function starts, it saves the old base pointer to the stack. So both the instruction pointer and the base pointer for the old stack, meaning if we overwrite this one, which we will, it will kind of mess up the whole stack, right? It will look for stuff in the wrong place. Copies the old stack pointer as a new base pointer. Push possible registers. Right. So the meaning of this for us, very odd, but is it 4? This means I miss information about the frames, right? The basics is not here. stack frames. Yeah, I might skip the next header because it's not useful anymore. This means that for every function that is run, a new bit of the stack is used. The old top of the stack will now be the base of the new stack frame, and the new top of the stack will be its top. When we later leave the function, this will all reverse, and the memory will not be in use anymore now. This means that for every function that is run, a new bit of the stack is used. The old top of the stack will now be the base of the new stack frame, and the new this is bad. It's not easy to understand. The old top of the stack, it's too much top and old and new and bottom. The old top of the stack will now be the base of the new stack frame, and here we will have first as said here, we will have the old instruction pointer, the old base pointer, so these are depend on the architecture, 32 bits, 64 bits, but since we already have E up here, I'm like, okay, whatever. And should I also lowercase these so they're the same? So I'm like, I typed this not so long ago, right? Yeah. Right, here's actually where this becomes interesting too. This image. but we'll simplify it. I'm like by the code instead of. It could be the compiler just knows that this register needs to be saved, or it can be that we coded it manually, depending on the level, right? So, and then function variables. And we don't have to specify more. This means that for every function that is run, a new bit of the stack is used. The old top of the stack will now be the base of the new stack frame. The old top of the stack. Let's make this right. Make it nicer to understand. Will be the base of the new stack frame. And there we will have the old instruction pointer, the old base pointer, and all the registers saved by the code, function variables. And I think I will actually, yeah, I didn't have that. I thought, did I copy the image when I thought I might want it? I didn't. So let's go back down, because I think it's useful still. So I'll probably change the next header. So we have saved registers, that's all of these. Then we have the interesting bit that I want to have here is that buffer 0 is at the bottom, but that's really for the next section. So let's see if I can drag it. Whoa. It copied a bit of it. It didn't copy the size change. Whatever. Stack frames. This means that for every function that is run, a new bit of the stack is used. The old top of the stack ESP will now be the base of the new stack frame, EVP. And here we will containing. This is not pretty. The stack frame will contain the old instruction pointer, the old base pointer, other registers saved by the code, compiler, user, compiler program, function variables, local variables. Right, better. The new top of the stack will be, this is from the old stuff, right? The new top of the stack will be the stack frames top. The new top of the stack ESP will be the stack frames top. We will later leave the function. Let's make a new section for this. We will later leave the function. This will all reverse, and the memory. Where did I put the image? It disappeared. I'm kind of sure. Yeah, this one. I'm adding the section here. So, as you can see in the image, a buffer would be addressed from the, it actually connects with other image too. Or more like this one. Yeah. I don't mind reusing the images. This is just text references, so I'm not copying an image and adding it several times. And when we put too much data into the buffer and get a buffer overflow, it will overwrite. What was previously put on the stack. So from the bottom, I don't have a good word there. As you can see in the image, a buffer would be addressed from the bottom. S. As you can see in the image, a buffer is addressed from the bottom. So I want the other image too. Let's skip the memory layout and just delete this section. No, we have the other bits here. So these two images, that and that, they're already gone. So let's cut this too, and let's just have text here. And then when we have use of the images, so from the images, a buffer is addressed from the bottom as the stack is bottom is not a good word since it says stack bottom here. I should make my own images so I could just do it whatever I want instead of just using someone else's. And this is really just a table, right? That's why this image is so much better. Maybe this is good enough for all of it. And I can delete these, but I want the numbers here. And the growing to lower memory addresses. This is really the point, that it's growing to lower from the bottom as the stack is growing to lower memory addresses. Is this okay and understandable? Higher memory addresses, user stack, stack bottom, stack top, and it grows toward lower memory addresses. So it's actually like the bottom of this buffer that is 0. Yeah, I think it's good enough. And when we put too much data into the buffer and get a buffer overflow, it will overwrite what was previously put on the stack. Both, well, first other variables, then other saved. Let's use the same words that I used here. Other saved registers, and then the old, the saved EBP and EIP. Let's forward them. The saved base pointer and instruction pointer. I think I haven't seen this clear instruction for it. That's why I'm doing this. When we later leave the function, this will reverse and memory. Yeah, I don't know what I was going to type. So now I text images for the text, images for the text. So this should be like a space here, definitely. Anyway, we will later leave the function. This will reverse and when the base pointer and instruction pointer are read back into the registers. When the saved base pointer and instruction are read back into the registers, we will get a segmentation fault if they don't contain usable values. There, so I put them in a bunch, in a clump. Maybe I should split them up. But we will get problems if the stack pointer is pointing somewhere crazy too, right? So they both need to have okay values. We will later leave the function. This will reverse, and the save base pointer and instruction pointer are read back into the registers. We'll reverse. What? Again. When we later leave the function, this will reverse. Let's do it like this. The saved base pointer and the instruction pointer are read back into the registers, and we will get segmentation fault if they don't contain usable values. Getting the right values there. Oh my goodness. I think I might switch. When your ears start itching. So, this is the oddest header ever, right? In the right place. Right? That's what we want. That's the next step. So let's hop back, because we're actually reading this. But I already had this image saved. And I didn't only have it from here. It's used in several places, so I don't know if this is the original place even. But I think it's the best one to have the actual memory in this direction. It makes it much more visible that this is 0 and this is 7. This means that we have now right access to the EIP. Allow specifying which memory does the EIP. However, to manipulate the register, we need the exact number of use. Determine the offset. So now they're going to do what I had earlier. So I'm thinking of switching up the order too. So here I have my notes on this. So I have hopped. Now we're going to exploit it. This is where we're really going now. But we didn't have a good header, that's why I put this. So it's all like going around and around there. But the base is really to understand how the program works. So I love these notes. This is Google, ChatGPT, other knowledge sources. I googled to confirm that this was what I thought. And with Google I mean also ChatGPT, Googling. Should it be GPTing now? I Google and GPT'd it. So, stack frames. So the explanation of this, it should be later. Exploring memory is a bit separate, but it is related to the tools that I list here. Yeah, so this is really the next bit here. Test input, right? And then non-repeating input. Then we want to see what it ended up with. So it's all logical. And then we have using shellcode, and then we have explaining the shellcode. So the program structure is before all of this. Let's see how long I can hold my button pressed there. Yeah, I'll move that later. This is what it is. It's really the memory layout bit there too. We need to get the right values. Into the right places. And then we start testing actual physically instead of just explaining the program structure, stack frames, how it will be in memory. Then we do test input and non-repeating input. And this is a part of exploring memory, really. But to know that we need non-repeating input, we need this bit first. This is where it should say exploiting. Because before this we were just like exploring generally. Is it a buffer overflow? Is there a buffer overflow? When we find a buffer overflow vulnerability, we need more information. Hopefully we can run a program in a debugger or attach it to debugger. I know I had this line there. Yeah, so let's cut this bit out. let's put it here instead. And we just list tools. And then we have some examples. Going to have examples. I don't know. I have to almost undo. Oh, I added an I. Infinite. Yeah, and these are headers. Maybe they shouldn't be headers. These are more like this, right? It looks odd when we have so much space there. This is also and then we have the long list of tools. Then we have non-repeating input using shellcode, example shellcode. This could be its own header on the same level. It's okay. Before it was squished in there. We use a number of nav instruction too. So this is connecting back. But the old value of the instruction point is saved in the stack. The function is called. And this is like before, so that's why I started typing out stuff on this. But to overwrite it, we need to know the organization and contents of the stack and how the instruction pointer is saved there. And this we had already. Is there a buffer overflow? Exploiting. I might move this again. Let's just skip it. Yeah, because I felt this was odd before. So when we find a buffer overflow vulnerability, we need more information. We can use different tools to explore memory, to debug and step through program execution. Maybe even no, I don't like it. This is better. Yeah, actually. That's okay. And then we just have this. And then it's logical. The simplest might be. More complex. No, it all hangs together. And we're going to add examples, of course. Then we have non-repeating input. And this is after now we know how the program is controlled, how stack frames work. Yeah, let's hop back. So, the offset is used to determine how many bytes are needed to overwrite the buffer. So, different input. Increasing the size to see if the program crashes. Then we can perform basic tests where we try different input, increasing the size to see if the program crashes. Checklist space we have. Right. Shellcode is a program code that contains instructions for an operation that we want the CPU to perform. The manual creation of shellcode will be discussed in more details in other modules, but to save some time first, we use Metasploit framework MSF that offers a Ruby script called pattern create that can help us determine the exact number of bytes to reach the EIP. It creates a unique string based on the length of bytes you specify to help determine the offset. So, USR, German's byte, well, pattern create. L 1200, pattern txt. So, let's see if this is our path. If this just works. So I don't think they use Kali. They use Parrot, right? Just checking that we're in the place. No feedback means function worked. So let's cat. And that's how it works. It just generates this pattern. And I already have this in my notes as part of the instruction here. So this is it, threading create. And this one is 500. So of course we didn't have to put it into the file, but that's kind of user share. Yes, the same path. No, we replace our use with a generated pattern and focus our attention on the EIP. Yeah, I should probably have done this. They have a file and they still print it with Python? Why? That's odd. Why create a file with it then? And then print cat the pattern? They could have just run the command without this and they would have catted the pattern. Well, really making a document for teaching other people this, right? So I'm thinking of adding it here. But we can make files. We understand how to do that without help, right? Right. So. So, let's see what we run before. Let's do this. And then we did run. And let's see if we can just use pattern.txt, right? Yeah, or we could do, sorry, wrong character. That might be better. Very obvious that it's not like, we don't want it to be an argument to it. Or rather, we want it to be an argument, not input. Let's just double check what do I have really up here. So I have these. I don't have anything else there. So now we have a number. Since this is not a unsecured VM, it's my normal Kali. I'm curious to see if it's different results every time, right? So what did they do? Yeah, they used Python for some reason, though they made a file here. When they could have just catted it that we did. The program being debugged has been started already, and they got the same number that we got. That's nice, right? Let's do info registers. Right. IR. And they just did one of them. We want all. I just saw that the third column is this made easier to read, right? Decimal mostly. And also minus. I don't think so. I think those are memory addresses or something, right? So, I'm just going to check what they do. Let's see the TIP displays. Well, we know what we're going to do, right? We're going to check what offset this is. Right, like this. So my example is this Q for query. Let's see what they say. Q for query. So confirming that the notes are correct, right? Always good to do. So Q. The same. So they have an image here for it too. So we know how many you used to add to get to the EIP. To override it and check if we have reached it as planned. Okay. I'm not running this because I've already done it so many times now. But I'm kind of thinking I need better notes, right? And let's do that. So when I did this, I was going for the instruction typing kind of thing that way. But now I'm more at make it a long text kind of thing. Right? So if we do a big C here, it will be easier to see. So we want to put the code in memory and then redirect execution to this memory. I'm just thinking, do I need to add anything here? So we're going that way here, right? But we're just confirming that it was correct output. So right, we could actually run this only because it's a good test to see that it's actually. I'm just a bit annoyed that we have to keep going in and out of this. Let's run it. Since we have the same numbers, we can just copy theirs. So yeah, we can't just copy theirs because they are using ancient Python, and my Python link goes to another place. So we have 66666666, and what I want to do is not to just look at this bit of memory, right? We want to see all of the memory, and I don't remember the GDB command to show a memory address, so P yeah, and also X. PX. So what if we do, yeah, and var name. So I missed that in my notes. Here there's and there's not here. So let's just add it, because I was like, there's a character, what character was it? No, I know. So let's do P and what if we do like things like this? Use a file command. What is file? So what if I do X? I think that the current address will be used. So it just didn't show anything. So let's try the one I had here. Oh, now I know. So that's of course for addresses, but this Here we need instead a $. So if we change this now to X, what happens then? And if we do X 200, we get more data from the memory. So this is when I want to use R2. It's so much easier and prettier output. Right, so sorry, let's actually do the rest of it too. So the thing that we actually need to do also is that, right? So here we have the 555s and the 66, so we can see it all now instead. And if we do I'm cheating. What was it? IF. No, that's so IR. It is I. So IR. And then we can see here stack pointer is CAF0. So CAF8, so it should be in the middle here. Like where it is, right? Or rather this way, because it's already got this bit. That's why it stopped. Yeah, because it did stop when we run it. So we can see the old stack frame, I guess it is actually. So if we do more than 200, so let's do 100 instead. And I'm assuming this is hex, right? Well, let's do actually 108. And let's, instead of that, do 98. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, so it doesn't change. Oh. Yeah. R2, thank you. So comparing this output, what we're just seeing on the screen here, 2. Let's see. Not here. Didn't I save that output? Yeah, so it's in one of the other ones. Also, I notice how hungry I am. I usually can't eat one of these pies whole, but now I'm on the last piece without noticing. Yeah, so not in there. Okay. I want this saved here. And this is GDB. XP. So the least thing I would do is to have a link, right? So GDB, and then I'm sure I switched here, right? So here we're on R2. IA to get a lot of random info. AFL, list the functions memory addresses. Like here is main, and here it's copy arg function. Then we're disassembling, and I put this as images because they're so colorful and nice, you know. Then we have AFL PDF to here let's see. IC to print strings. Yeah, DB for adding a breakpoint or listing them when we only do it, right? DC to continue. DR. List of registers possibly there. Yeah. DS is to like execute one line. We're printing the breakpoints, adding a breakpoint, printing the breakpoints. Now we're at it. So PX, PXW, you have different formats print out, and you have this nice decoded one too. Maybe GDB can do it, but I don't know how. PXA is the one I've used because it shows symbols. So here is where RSP is, RBP. So if we just do this, the same thing. Actually, let's open a new tab, and we end up in the same directory anyway, and now we just R2, and I've already done it with this program. of course, right? So, if we run it, pxa at rsp, right? We can remember this. Actually, this is what I wanted. So we wanted more information in this file. Now this one should be easier to find again, and I recognized it when I saw it, so now, oh gosh, I tabbed to the VM, then I tried control tabbing, and I was in the wrong program, so I tabbed to another of the VMs tab. I don't like VMware having tabs up for all the machines you have, but it is like that. Yeah, the PXR is kinda complicated. But we have also the detailed ones. So how do these differ really? So I need my list. Oh, for R2 I need my list. So rerunning it with arguments. How did I do it? OOD. Right, so let's do OOD, and let's remember what it was called. What did we just run? Here. So I must have pasted something very odd, like a new line. Now I could control it at least. Actually, let's just do it here. Right? Now I know what's wrong, you know. I copied the first one. Then I run. Here is the correct one, because they have old Python when they do stuff. I mean, HackTheBox isn't that old, right? It's not as old as Python 3, is it? Can this page be that old? So let's try OD again. Maybe it was this, it was the odd thing. Nah. So let's I saw this message still. I don't know what it is really. Bin relax apply true. Ebin cache true. So what if I do like DC now? So we have the correct address here too. It's 66666666. So now we can use PXA, right? And I just added it to my notes too. So at RSP. So it was just weird 32-bit. So this is how pretty it looks. And also we can see the colors. So let's now actually find the right place in memory. So let's try -100. So I can see the 6s now. And the 5s. Yeah, it's all there now. 5, 5, 5, 5, 5. All the U's. And then the 6, 6, 6, 6 for the F's, lowercase f apparently. So what if we do 1, 1, 0? So this one we moved where these are. It worked, right? So how many lines of U's do we have? I guess there'll be a lot of them, right? Now we only have U's. All of it. We've lost connection to the other one, but it's 1,200 U's, right? Or what was it? A lot of them anyway, in the Python bit there. Yeah, so I'm thinking let's make some kind of notes from this information, right? 1036. Use. So we've twice confirmed. I'm thinking my notes are not like complete, so we need to add stuff. So here, example. And we will like steal our example or theirs. Should we do R2 or... Yeah, so this is the prompt where we actually did the first steps, right? I'm just reading. It's a bit funny. How I did several times with the Python. Come on. Am I like blind not finding the one here? So confirm. Confirm buffer overflow. Then we have check length to instruction pointer. Yeah, I'll have to leave soon. So last week I got this from the trainer. Kinda nice. 1 terabyte SSD disk. I don't have a that big one, so it's for me it's like, should I pay you? What? Apparently he works at a school where they will just as IT. So that's nice. Let's see, we did this one. That reminds me, something I need to fix before I go there too, and it's 1654. Parse error near parenthesis. So why did I do it again? I don't know, but this is the line I wanted to copy. So we didn't do it as they did exactly, but we did it very similar, right? We don't need to cat it, we know what it is. So I don't like that I have a lot of GDB here. I should have used R2 to practice also. Apparently R2 is like a newer version, right? It's newer. And this is a run command. I'm just pasting the things I copy into the notes. And then we get this. And then I just rerun it to test that we got the same thing. Well, as long as it's selected still, it's kind of easy to find where this is. I Control C it instead of Shift Control C. It happens. So we have this, and then we're going to add the test, the same one. So after running it, I also looked at this, but then we quit and we run this. Alright, I'm not saving all of it. So, test position. So, lots of the same again. As long as I don't forget to do Shift Control or parenthesis for print in Python. I was copying, that's my excuse. And I have changed my notes to be modern. Starting program. So, this is so far, right? What else did we do? We checked in memory. This was just our thoughts to test this. And we tested in memory with R2. So that's all we did, really. We got a nice example out of it. And I can't switch to this. Right. Yeah, so we're like at the end of it. I guess we should finish it, even if we have 2 minutes. Now we see that we have overridden EIP. Next, we have to find out how much space we have for our shellcode. Right. Yeah. So, yay. We can overwrite. We can set EIP. Find out how much space we have for shellcode. Yeah, next up. Which then executes the commands we intend. As we control the IP now, we will later override it with the address pointing to our shellcode's beginning. And then there's VPN stuff. And connect. And examine the registers and submit the address of EBP as the answer. And we can SSH. So we've done this before, but we don't have enough time. I might do this just quickly off the stream, because we need to log into theirs to have their addresses. So, next time, we're going to continue. And we're going to make sure, yeah, that we have all the things in the notes.